welcome. It's my pleasure today to introduce Dr. Omur Arslan. Dr. Arslan is currently an assistant professor at the Department of Mechanical Engineering at Eindhoven University of Technology in Netherlands. He got his PhD in University of Pennsylvania in electrical and systems engineering. And before he got his BS and MS degrees from Middle East Technical University and Bilkent University, respectively, both in electrical and electronics engineering. And his research interests include robotics, motion planning, multi-robot systems, sensor networks, machine learning, and machine perception. And today we will get the chance to learn more about his work. So I would like to thank him for accepting our invitation and joining us today. So without further ado, I would like to give the mic to you, Dr. Arslan.
Thank you very much, Tuğçe, and thank you very much for the invitation. It's a great pleasure to meet with the younger people always, to share some of the ideas and some of the work we do. So today I will talk about some of the new perspectives we work on for the robot motion planning and control, especially the connection with motion prediction and the motion planning. And it will be more on the philosophical discussion and demonstrating some of the maybe applications to highlight why we need motion prediction for safe robot autonomy. And you see our campus actually, it's also relatively small in size, but it's densely populated because Netherlands is a small country. Overall, it's very densely populated and it's pretty flat. You can see a very long horizon, especially if you are in this building in the 10th floor. I am now in this building here, which is the mechanical engineering. And my background is in electrical engineering, but basically since I do work on robotics, I can be anywhere, you know, in electrical engineering, mechanical or computer science. So I believe that that multidisciplinary aspect of the robotics is very nice and kind of a very challenging sometimes because you need to know many things and relate many other disciplines all together to come up with a nice novel solution. And let's see if my thing works. Yes. So why robotics? Because I believe that everyone is aware about this popular, you know, news about the robotics, how they are going to change our lives from mobility. So with the self-driving cars to autonomous, you know, deliveries, maybe, you know, in the warehouse. Also, of course, the most important thing is they will play a key role for the people in the long run for elderly care, minimizing some kind of, you know, dangerous tasks for people. And all of them are, of course, because of one thing, these platforms provide autonomous motion. So these platforms ideally need to understand what they are seeing, and they can come up with some plan and execute it and perform diverse set of tasks. The idea is nice, but there are some challenges. When you think about self-driving cars now, the technology is not quite there. And when you look at the news, for example, Cruise, it's a self-driving company supported by the General, you know, Motors and the Ford. They decided to close that technology now. Why it's happening? Because that unique capability comes with a unique challenge, safe autonomy. So without ensuring safety of these autonomous motions, you cannot deploy these technologies around people. And it brings that, you know, the initiative, how we can, you know, ensure we can build reliable and dependable robotics technologies that can be safely deployed around people. And that is main research, you know, focus I have currently. And I work on the algorithmic side. So I am not interested in designing a new hardware because there are many people doing this kind of work. And it's relatively, you know, very established field of research, also technology domain. So, but when we look from the algorithmic perspective, how to make these machines smart, it is still a challenge. And I usually look at the fundamental and applied research for safe robot autonomy and active perception, which means that, you know, making a link between the decisions you make for your control and also for the perception. So there's a nice interplay when we think about the mobile robotics between perception and action. In order to do some, take some action decision, you need to use the perception. And in order to get good perception about the environment, understand how it's structured, even build a map, you need action. So this interplay, I believe, a nice domain for research. And I particularly focus on the motion prediction for motion planning, because when it comes to safety, you cannot just say that I don't have a collision right at that moment, and it will ensure that your motion is safe. Because when you think about driving, if you are driving at a certain speed and if you want to stop, it doesn't happen immediately. And it plays a kind of a key role about ego motion estimation of your vehicle, and also the motion estimation of the other people, maybe other autonomous agents in the environment. Of course, perception plays a key role. So when you think about a mobile platform, you cannot really solve perception separately, motion planning separately, control separately, and put them together and expect that it will work. Unfortunately, it doesn't work in practice. We know it very well. And so how we can design motion planning algorithms that will be also aware about the limitation of the perception. So this is, I believe, another promising research direction. I put some effort on that direction as well. And then the other challenge is the dynamic environment. So we have pretty, mature understanding of how to do motion planning perception about the static environments. But when you go to a dynamic environment, all of a sudden perception and planning becomes a challenge. And these are actually all linked from my perspective. In order to solve all of them, you need to approach this perception prediction and planning and control in a kind of a holistic way. If you want to find a robust solution, you need to integrate them. In parallel to these three aspects, I also work on the active perception in multi-sensor network setting, like you can think about a distributed camera network. They need to get some surveillance information about the environment and how we can do this effectively, because usually sharing the raw sensory information between these agents, it's not possible because of the communication and the power limits. So how we can come up with smart way of doing it in a systematic way so that they will obtain some global understanding of the environment just using their local observations and the interaction between them. Overall, I say that I work on computational robotics research, and that is the name of my lab here. It's the core lab. So I have been at Eindhoven University for the last 3 years. So it takes lots of efforts to bring these things, in really physical setting. And we are still setting up our lab infrastructure. Currently, we have some mobile platforms like scaled cars, some simple, education platforms like turtle robots, and we have motion capture system to always get some ground truth, how we can justify that our algorithms does the correct things. We have multiple cameras, also provide some side information, because robotics, the autonomy for a robot doesn't need to be like a human, in the sense that it should be only self-sufficient. The interaction with the environment is very essential, and it's the flexibility, because you can then do much more effective solution with limited computation and perception skills if there is some kind of a side information coming from the environment. Because of that, I also look at the interaction between the robot and the environment. And we have some new member gonna join in our lab in the new year, mobile platform with the robotic arm, so that we can really go from mobile navigation to a little bit mobile manipulation like task. And at the end, hardware doesn't work its job by itself, so we need people. So I work actively with students at the master level, at the PhD level, and sometimes with the bachelor students as well. So going back to today's topic, so I will basically talk about motion prediction for safe robot motion planning and control. And I assume that people have maybe different understanding of what does it mean robot motion planning and control. So let me start with that problem first. So robot motion planning and control basically is nothing but you have a platform like an autonomous driving car or a mobile service robot, and you want to go, let's say, a simple task from a given position to a destination. You have some place of them, part of the environment you can use for traverse, so you can move, and some parts you are not allowed to move because they are obstacles or there can be, other constraints. And in a very abstract setting, it can be taught like finding the control inputs, these U at every time instance, such that it will take you, when you apply this control on your robot to the destination. Of course, there are a couple of challenges here. Directly finding the control to solve your problem, it can be computationally hard, sometimes technically, not possible. And the other challenge is when you have these control decided ahead of executing it, with specific timing, if something goes wrong on the way, you need to do replanning. And this is a kind of a challenge. We see that in practice, this kind of approach doesn't work. And how we solve, when we look at the standard approach, they solve this problem in 2 steps. First, let's forget about the actual robot dynamics. Maybe consider a very simple system. It can be controlled in terms of its position. It can go in any direction you want. And you want to plan a motion, potentially a path, by taking into account the environment geometry. So you want to avoid from the obstacle. So you find a path from initial position to the goal. And the thing is, you need to execute this on the real platform. How you can do it by applying some low-level control, which will take care of the robot dynamics given, towards a kind of a specific location. But when we are doing this motion control, most of the time we also forget about the constraints, like the safety constraints. So safety is mainly handled with the high-level planner, and the stability of the motion is handled with the low-level control. But the gap between them can cause some issues. Can you make sure that can you execute the high-level plan in a safe way? So there is this gap. Closing this gap requires lots of research. We have early attempts. For example, when we look at the earlier work on applying these high-level plans with the low-level motion control, you can use a kind of a functional representation using a potential field, for example. The idea is, can I convert the geometric information about the environment into a function such that it will have a let's say, global unique minimum at the destination location, and it will take maximum values, most of the time infinite, when you have the collision, like on the boundary of the obstacles, and you follow the gradient field to reach the destination location without even planning a path, because it specifies what's supposed to be the control input at any given location. And it can be easily adapted to, robot dynamics. So we like gradient fields. The challenge here is finding a functional representation of the environment. It's hard. So it works in very simple setting, but when you think about very complex environments, unfortunately, it doesn't work. How you can, overcome this problem? Yeah, I suggest that, instead of linking the environment geometry to robot dynamics, let's find a geometric representation of the robot motion. So don't worry about the dynamics much, but find a representation that will tell what will be the robot motion like in terms of a geometric description. Today, I will show one method, and then this geometric representation can be used to, safely execute the motion you have. And there are plenty of work in these domains, how to make the link between the high-level planning and low-level planning. So I'm not giving a survey, work or the lecture on this topic, but I want to share my perspective. So I think the right way of doing the link is through the geometry. So we need to turn robot dynamics, robot motion into a geometric form. So what does it mean? When I think about robot control, I usually think about a robotic system. You have a control, very well established, maybe, design you have in mind to execute a reference task. It can be like, reaching a point. So here, when you apply this to your robot, starting from a given, configuration, you can reach the destination. And this is the motion. And what we mainly worry about is the safety of this motion, because you can have obstacles around. And one way is, checking safety is, of course, you can go along this motion because you have, let's suppose that you have the very precise model of your robot, your controller. You can simulate your motion. You can get this trajectory. And in order to verify the safety, you need to check at every time instance. So there is not a systematic way to, verify that this entire motion will be safe unless you do something else. And then motion prediction becomes a kind of a way to do this. The idea of motion prediction is simply, can I find a simple geometric shape that will just, describe my motion instead of the motion trajectory? Can I get some idea about what will be my motion range while I am reaching to destination under that specific control, such that I can use this motion range. If it's simple, accurate, I can use it for the safety assessment. Then you can think about, in a dynamic environment, there are many agents, they are moving. If you have some idea about how they are moving, under what kind of control, with which kind of reference, you can come up with these kind of, prediction ideas, and you can plan the motion of your robot, not only based on the position, but intended motion in the future, which usually works more effective in practice, and how to verify that it will be really correct algorithmically. So overall, I guess if I want to summarize, the objective is how we can relate the geometry of the robot motion to the environment in order to, ensure the safety of robot motion. Of course, it requires, maybe many different, it may be possible to solve this problem in many different ways. And I say that one potential option is find a motion set that will be specific to the controller you use. Starting from any initial condition, it will contain the motion you have. And here the challenge is, what should be that motion set? It should be simple, because we want to, at the end, use it for collision checking. And it should be also accurate, because if it's too conservative, like, a potential motion prediction is the entire space, it's not informative. So it should be also informative about the motion and accurately describing the motion itself. So this is a general, research direction. You can do many things, and I will show you a couple of examples in the following slide. I will start with PhD control. So if you are doing PhD, you need to go a little bit, more than just proportional derivative control. So I believe people who are able to read math and have some control background can understand what these equation means. Basically, you have a second order system, and you can use the position and velocity of that system to stabilize at a particular point. And I'm usually interested in more complex dynamics like nth order system. You are not only using the position, velocity, maybe acceleration, higher order derivatives. This is one way of, making link between non-holonomic system. We will see an example in the following slide, like a differential drive robot, which cannot be able to, go sideways. So when it comes to controlling it, you cannot consider them as fully actuated, but by increasing the, their mathematical models, like the order of, dynamics level, then it can be modeled like a fully actuated system with the cost of, higher order equation of motion. And for such system, you can estimate the motion using some standard tools. Again, people familiar with the Lyapunov stability theory can understand this construction very easily. Basically, using a function, Lyapunov function, you can look at the Lyapunov level set, and you can see that the motion will be inside these level sets for all future time. And when you make progress towards the destination, this motion prediction also shrinks. So this is a very nice property of the Lyapunov level set, but the problem is it's a little bit conservative. It describes more than what it's supposed to do. Recently, we developed new tools, Vandermonde simplices. So it is more tailored towards what the control you have, also what is the initial condition. you have as a starting point for your system, and it can capture exactly the same motion much more accurately. And we will see why it's critical when it comes to motion planning. But before that, maybe to show a disadvantage of the Lyapunov ellipsoid, here you see a second order system starting from arbitrary positions with different velocities. All of them share the same energy level mechanically, and the corresponding Lyapunov motion prediction is the same for all of them. So it cannot really precisely describe what is your motion is, but for a set of initial condition, it tells the expected motion. And this is related with invariance property we like about these tools in stability. But when it comes to expressing the motion of a robot, I believe that we need to give up this positive invariance property, which means that I just need to be able to express the motion for the state I currently have, for my robotic system. And these kind of constructions can be also extended to higher order system. And the nice thing is these are also analytical, representation, almost like, Lyapunov ellipsoid. So that makes it very attractive tool to describe, robot motion, relate the robot dynamics to the, environment geometry. And in order to show that, I will talk about the path following task. So here you are, in an environment with an obstacle, and you want to safely follow this path. How you can do this? There are many ways of doing it, and I will tell one nice new option by, creating a feedback time parameterization of a path on the fly based on the expected motion of the robot and the environment. So how does it work? You have an environment, you use a reference planner like any search methods, if you are familiar, A star, other, or the sampling based methods like RRTs, rapidly exploring random trees, and you come up, or a user specified such a reference path. It's also possible, human robot interaction, and you want to follow this path with a robot. And the thing is, you also can come up with some standard way of controlling your robot. If you forget about your obstacle, you know how to stabilize it around a particular point. And with motion prediction, we can also describe the geometry of that expected motion. And then the key thing is, you have the robot position, you have a particular path point you want to reach. You can estimate the predicted motion of the robot while reaching to that destination. If that predicted motion is safe, even more than just verifying, like a Boolean decision, yes or no, if you can measure that in a kind of a continuous measure, like distance to collision, here we do with the safety assessment, you can also describe how you can change this path parameter, because at the end, you want to reach the end of the path. So this gap between the predicted motion and the obstacle can be used to change how fast you want to move along this path. If there is a large opening, you will be able to, have very aggressive motions. And when you are approaching the obstacle, you will just slow down. And we want to do this in a systematic way instead of, writing if then else, comment in your construction. And when we look at the motion of a second order system, just using this philosophy, with the PhD control. So we just take the PhD control and the corresponding motion prediction, and we applied different ways of doing the motion prediction, because we also wonder what is the role of motion prediction in the robot motion. And we have two options, Lyapunov ellipsoid and the fundamental simplicities. Also, when it comes to feedback control, you can just provide maybe the reference position where you want to go. The other option is, since we are creating how the path point will evolve, you can also provide the reference velocity as a extra information, and we can check the resulting motion. Here on the left, you will see the path following behavior with the motion prediction. The yellow region is the predicted motion when you are reaching that red point. it evolves along the path, and it always will be, safe in the sense that it doesn't have intersection with the obstacle. And this gap is ensuring that we can really, safely move along this path. And when there is an open region, it allows the robot to speed up. And when you get close to the obstacle, you slow down. And one thing to observe is when you are moving on the corridor, since the motion prediction is really symmetric, it doesn't only worry about, collisions waiting you ahead of you, but also the sideway collisions, which are less relevant to your motion. And I believe that that is one limitation of the, Lyapunov ellipsoid or any conservative motion prediction. So when we look at the effect of velocity feedback, because now you can also use the velocity, you have better tracking performance in the sense that you can be almost on top of the path point when you don't change the path, significantly. And this helps us more aggressive motion. You can have a faster, less travel time to reach the destination. And the other thing I believe compared to the previous example is, I can get rid of this and play. Yeah. The meaning of the motion prediction here becomes like, since there is no position error, it's really because of your velocity, you predict a motion, and that predicted motion is nothing but what will be the space required for your robot to stop. So in practice, when we look, people use like time to collision like measures. These are related with your velocity and so on, but you usually assume that, when you are estimating this time to collision, velocity will stay constant. Here, we really take into account the control information so that it's really the space required to stop instead of, what will be the time remaining for the collision. And what happens if we continue with the Vandermonte simplicity? The story is completely different. When you have the position feedback already, you get good enough path motion because the motion prediction is more accurate. You relate the robot motion to the environment more accurately, and it yields us more aggressive motion. And if we have the velocity feedback, as expected, you will be on top of the, the curve most of the time. And the predicted motion have, again, similar meaning. What will be the space required to stop before collision? And it is, again, significantly less conservative compared to Lyapunov ellipsoid. Also, it is very aligned with your intended motion direction. So you don't worry about the sideways walk collisions anymore. And when we run the same thing with the third order dynamics, now you don't only control the acceleration, but how the, the derivative of acceleration changes. It becomes much more challenging, and the path planner slows down the system based on the predicted motion so that it can execute the motion, a high level task safely. So I think there are many ways to do these kind of things, but this is the one way of formally verifying that, without doing so much tweaking, you can really use the motion prediction for adjusting and, foreseeing potential danger before really facing with that. So because of that, I believe motion prediction plays a key role in safe robot motion design. So, of course, this was the initial development. We want to move more towards, actual robots, so which may not have really, fully actuated robot dynamics. And we recently look at how we can look also, do the motion prediction for more standard robot platforms like, unicycles. These are the mainly differential derived platforms used a lot on the warehouses, maybe a Roomba robot that cleans your your house. And basically you have the position and orientation of a system, and you can control the forward velocity, rotation angle, but you cannot go sideways. That is the limit. We just pick one control policy from the literature, which is very established, used a lot in the practice, because we don't want to reinvent the wheel, but how we can do the motion prediction. And in brief, the idea is if you want to reach a destination point, you need to turn towards that destination and move towards it when it's possible. So you inherently, decrease your Euclidean distance to goal. And this comes with this Lyapunov-like, motion prediction. So while reaching the destination with a unicycle, you can perform Lyapunov-like motion prediction using these circular regions. But we see that we can do much more better because we also have the nice orientation control. We always want to keep looking towards the target location, and we combine these two ideas, just take a cone towards the goal and take the intersection of this cone with the Lyapunov set, and you get a better construction. Actually, you can do something much more better because this cone already allows you to apply the Lyapunov motion prediction a little bit in the future, and you get much accurate prediction of your motion that can be more relevant when you are moving around the obstacle, and you can use the structure of the control to make it even accurate. But sometimes you need to give up some other nice properties like convexity, and it brings another question: up to which level I should be increasing this accuracy? Is there a limit? Because the best you can do is the actual trajectory, but we already know that it is not the right way of checking for safety. So there will be always a trade-off between the accuracy of this motion prediction. It will help with the motion design up to a certain level, but after certain level, it wouldn't pay off doing this motion prediction, more accurate. And here the correct, comparison of these methods. And from our observation, this ice cream cone was much more better than many of the conservative ones, also more accurate, truncated version. And we check, we applied these ideas instead of the time governors. Now we use the reference governor. The idea of the reference governor is you are not changing the temporal, specification of the plan, but maybe sometimes the geometric specification. So you have a freedom to change the direction of motion if you want. And the starting point, again, is a high-level plan. We have a plan, a vector field plan around the reference path. And this is designed for a fully actuated system. So a kinematic system, it can go sideways as well. And we want to execute it on a unicycle, which cannot go sideways. And this interface between the high-level planning and low-level control, we established through reference governor and this safety assessment based on the motion prediction. And from our perspective, this is a kind of a nice bidirectional planning control interface such that it can guarantee that whatever you plan can be realized with the low-level control in a safe way. So the safety of the high-level plan can be transferred to the low-level plan, if you use the motion prediction. Again, we did some initial simulation studies to see, the role of motion prediction. Again, accurate motion prediction yields faster motion, but if you do more than enough, it doesn't pay off much. So it only increases the computational cost of doing the, this safety assessment, but at the end, the motion doesn't change significantly. So the current work is going more on the direction of, how we can apply these ideas in real physical systems. So we are trying to make it with sensors. So the perception part, it is one thing I think that, very important, not only interfacing planning and control, but interfacing planning and control with perception, because robotics is done with perception. Otherwise, it will be only a kind of a case study. You can do lots of maths, but not, any impact on practice. So now I believe that I will slowly wrap up, and it will give us some time to discussion. Some concluding remarks. So I think motion prediction, from my perspective, as a person working on, robot motion planning, it is a way to relate the geometry of the robot motion to the geometry of the environment. which can be done many different ways, but motion prediction, especially feedback motion prediction, by keeping in mind the control you are applying, it's a very promising direction. And I will continue pushing in that direction. I encourage people to work on these kind of things because there are many different robotic platforms and they need these kind of tools to use, for reactive planning. And it offers a very informative safety certificate. So the existing tools are like instantaneous collisions, time to collisions, but these are a little bit heuristic made up things. And motion prediction allows us to really, if it's accurate and it's easy to compute, it can be an effective way of justifying, autonomous motion you are designing. And it's currently enables us to do the integrated robot motion planning and control. Classically, they are decoupled. And when you want to run them together, there are essential issues. And when you do this in an integrated way, you ensure the increased robustness. And potential open challenges may be, future research direction. As I told you, I will go on the perception side. So I encourage many of you to also look from that perspective, how we can integrate perception, prediction, and planning all together with learning as well. So our systems always, interact with the environment, gets new experience. Why not use that information back in the prediction? That is very, promising direction as well. It can be related with machine learning a lot. So the other thing, I believe that planning in dynamic environments is challenging in the sense that justifying that an algorithm you design will work in dynamic environment. Yeah, how to approach that problem as a starting point. It is a challenging, but overall, the dynamic environments comes up many perception planning and the prediction challenges. And potentials, I believe that many standard robot control methods, we know the stability properties, but they don't have this kind of prediction tool. And we are started building some, for the mobile platforms like the drones, but there can be many other settings like manipulators, how we can do this kind of prediction for this. In addition to ego motion prediction, of course, allocentric motion prediction is also important. So overall, the other thing, if you are interested in, I have another talk about, informative safety assessment I gave at Matthew Romar Center online. It's available on YouTube. If you are interested in this topic, it can give slightly different perspective about, creating these kind of tools for autonomous robot motion design. And going back to my starting point, there is a huge, potential and lots of research challenge to link the high-level planning to the low-level motion control. And when I look at the literature, there is, 30 years gap between the navigation functions and, our recent work. There are many promising tools, but we don't have the method how to solve that problem yet. And that is a lack, a bottleneck in front of many of the technologies, like why we don't have the autonomous driving yet. We don't know the link between planning and control and also perception. So please be open and, look at this problem a little bit at the conceptual level and try to come up with your own philosophical approach and your own challenge. And if you have any question, I will be happy to answer them now.
Thank you very much, Dr. Arslan. Let's turn to the audience. Any questions from our audience? Maybe I can start, but as someone from outside the field, this might be maybe, I don't know.
All questions are welcome, so there's no right or wrong question.
Yeah.
It's the exchange of, ideas.
So what is the current then So I understand this geometric representation. You mentioned there is a gap of 30 years. And of course, people are trying to find a solution between high-level planning and low-level motion control. What are the current common practices being applied with autonomous cars, for example? Because there are, experimentals, some of them are closing, but there are some companies still trying to achieve this. So maybe at a very high level that we can understand, or I can understand how they are trying to achieve this other than using this geometric representation approach.
Yes, so actually many state of the approach right now, it follows slightly different way. The link to control is even weaker there because they mainly tries to come up with a trajectory, which is a time parameterized path. And it can be really complex in the sense that, it can represent very complex maneuvers. And the approach is we can solve this problem relying on high computational power, because when you think about a car, you can put really a strong computer there. It can do these kind of calculations for you. But when you think about a cleaning robot, which has, very limited battery and maybe very limited, computation power, it's not possible. So the advantage of, I believe that was also the promise why people thought that, we can solve this autonomous driving problem really fast because we can compute. And the current approach unfortunately hit the limits because computing is, yes, it is important. We have many, advanced perception algorithm that tells us about the environment. But at the end, you design an algorithm and you need to verify it's safe. We don't have ways to verify, in a kind of a computationally efficient way, because there are also many other existing formal methods, if you give a month, they can check if an action is correct, safe, but I need to execute it in the given, 5 milliseconds. And that is really the driving force for my research, how we can create some tools that can be computed almost instantaneously. And because of that, I give up very precise representation of the, these motion instead of trajectories, because I know that safety verification requires lots of computation. But if you have some rough idea, and if this rough description is easy, like triangles here, basically, then you can compute them, instantaneously, and you can make these verification on the fly. And that is, I believe, the notion of feedback here. So usually when you look at the literature, they talk about the motion prediction as well. So this is not a new thing, but the tools are very primitive. You are assuming that, for example, you want to predict the motion of a pedestrian. What is the standard model now? You assume that the pedestrian walks in certain direction, fixed direction at a constant velocity, and you are trying to understand what is that direction and the velocity. And you assume that it will be constant for a given certain time, which is not valid. The motion of the pedestrian is affected by many things happening around, and it is related with the control that person, follows. So some kind of decision rules they have in mind. Then I think that this is a good opportunity. Unfortunately, it is not the current practice. And I'm happy for that, because if it was the current practice, I need to find a new research direction, right? So I'm really trying to bring these new perspectives. It is a little bit orthogonal to what is the current, technology is based on, because I know that it doesn't work. It wouldn't work from my perspective, and I need to be ready for the future.
Very interesting.
So state of the art is not a grand truth for me in summary. I try to go over the state of the art. What will be the tools of the future?
Yeah.
And that is, I believe, the driving force for our research, right?
Yeah, very interesting.
So this is mainly a vision and more like a philosophical, perspective than solving a practical challenge today.
I understand. Okay, very interesting. Yeah. Any
other
questions
question
from the audience? Don't be shy. Nothing at all?
So there are 19 other people.
Yeah, some left, I guess.
So anyone working on these kind of topics, robotics, mobile robotics, perception?
No one. I know we have students doing those kind of work, but maybe they didn't join today. No one?
Okay, then.
I'm also checking the chat, but yeah, okay.
So you can share maybe also the presentation.
I will. Yeah,
students they can reach me also offline. Please feel free to reach me if you find these kind of topics interesting. Then we can share ideas, look how we can work together. And if you can also share with me, I'm also planning to share with a broader audience, so that this is a kind of a research direction I promote for people to work on.
Yes, I will very happily do as soon as the recording is available to me. Okay.
Yeah.
Thank you very much, Dr. Arslan, for this interesting topic. So I'm really curious about the future as well, how this will proceed. So thank you very much for sharing this with us, and thank you again for coming, for joining and accepting our invitation. Hopefully we will host you physically one day as well in the future in our campus. That would be really great to do.
Sure, definitely. It's always interesting for me to meet with the people, and hopefully in the future there will be more convincing results, because I'm pushing in that direction, so that people might have questions, wonder why it works. And that was the reason today I discussed.
Okay, thank you very much.
Have a nice day, everyone.
Thank you.
Happy New Year.
Nice day, everyone. Thank you.
İyi günler hocam.
İyi günler hocam. Çok teşekkürler katıldığınız için tekrar.
Rica ederim.